Hey all, and so we're going to look at another set of proofs involving sets. I'm going to do an example here, and then you'll have another homework problem set as well as another presentation to practice with. So, quick review from last time. To prove that two sets are equal, we've proved that the first is a subset of the second, and then the second's a subset of the first, therefore they must be the same set. And generally, as these problems get more challenging, one of these will be easier than the other. And sometimes you can guess which one that's going to be. Sometimes you just have to get started. But I am warning you that sometimes one will be very straightforward, which is what we're going to see in this example. And that might mean, though, that the other one is substantially more difficult. So here, prove that 12a plus 25b, where a and b are integers, is equal to all of the integers. So what this is saying is that prove that every integer can be written as 12a plus 25b. Now, the first step, in this case, this one is the relatively straightforward step. So what we're going to do here is we're going to say that x is an element of 12a plus 25b, where a and b are integers. So what that means here is that x is equal to 12a plus 25b for some a and b in the integers. And our goal is to show that that element is also in the second set. So we just want to show that x is in the integers, which is pretty straightforward, because all we can say is that by closure, and this is why I do stress closure so much, it sometimes makes proofs really easy, 12a plus 25b is an integer. So therefore, x is an integer. We now have shown that these two are subsets like this. So nice thing, pretty straightforward there. Now the other way is a little bit trickier. So what we're going to say then is we're going to start with x is an integer and see if we can show that it can be written as 12a plus 25b. Now, what I want to first start with is from a previous set of notes. So recall, this is what it's really helpful to go back and look at some of our older things, is that hopefully, maybe this made you think about our greatest common divisor of a and b can always be written as AK plus BL for some K and L in the integers. So we've done this in our notes. Now, why is this helpful? Well, in this case, we're looking at something in these positions are given. So greatest common divisor of 12 and 25 equals 12k plus 25l for some k and l. Now, we also can just use our mathematical memory to know that the greatest common divisor of 12 and 25 is just 1, since they are relatively prime. So now we know that 1 is equal to 12k plus 25l for some k and l in the integers. Now here's where we want to come back to this idea of x. Well, x is an integer, and if I multiply both sides of this equation, I get that x is equal to x times 12k plus 25l. And then I can distribute and give that x is equal to 12 times xk plus 25 times xl, and now we know that xk can be equal to an integer by closure, so I'll call that a, and xl is equal to an integer b by closure. So now we know that x is equal to 12a plus 25b, which means that x is an element of the set 12a plus 25b, where a and b are integers. Since we've now shown the subset the other way, they must therefore be equal. So we can finish up. Therefore, the set 12a plus 25b, a and b are in the integers, is equal to the integers. And this would be true, in fact, for anything 12 and 25. Those numbers could be anything as long as they're relatively prime. This same proof would work. Again, let me know if you have any questions from the two problem sets in Chapter 8, and I'm available by email in the comments or on a Zoom chat. Talk to you later.